At the beginning, I will tell you something about the energy importance of triacylglycerols. Yes, how many energy we can store in triacylglycerols, why they are the best way how to store energy, and then the majority about beta-oxidation and ketone bodies. So, what type of storage compounds do you think we have in our body? We have triacylglycerols, that are this. What other storage compounds we have? Glycogen. Do we have some other? Ketone body, that's not a storage compound. It's produced during fasting to gain energy, but it's not a storage compound. Only these two we have. Only triacylglycerols and glycogen, only these two compounds are storage compounds, yes? There is no protein that can be used to gain energy without any harm effect, yes? For if you degrade some protein in the body, it will impair some function, yes? Of course, during fasting, you can degrade muscle proteins, but you will be weaker than normal, yes? During fasting, you can degrade some proteins in plasma, but you will have impaired transport of some compounds in plasma, yes? Therefore, we have only two storage compounds, and none of them is protein, yes? Triacylglycerol are the main storage compound in the human body. Why they are so good? For in their molecule, triacylglycerol consists of 3 fatty acids, 1 glycerol, and the fatty acids, that's only carbon and hydrogen. So they are reduced, and the more reduced the compound is, the more energy you can gain from it. If you compare, for example, the glucose and palmitate, in glucose you have how many oxygen atoms? 6. And you have there 6 carbon atoms and 12 hydrogen atoms. In palmitate, you have 16 carbon atoms, 31 hydrogen atoms, and only 2 oxygen atoms, yes? So in palmitate and other fatty acids, you have a lot of carbon, a lot of hydrogen, so you can gain a lot of electrons that you can use in electron transport chain, yes? In 1 gram of fat has 6 times more energy than 1 gram of glycogen, yes? So 6 times more energy if you have the same weight. And by complete oxidation of 1 gram of fatty acid, you gain about 38 kilojoules. The same amount of saccharides, of proteins, give you only 17 kilojoules, yes? So triacylglycerols are the best way how to store energy. Here you have the list. If you are a man, you have 70 kilograms, you have so high energy amount in triacylglycerols, yes? And in proteins, you have only 10,000 kilojoules, yes? So you see 40 times more in triacylglycerols. In glycogen, you have only 2,500 kilojoules. And in blood glucose, you have only 170 kilojoules, yes? So we can survive starvation only due to triacylglycerols. The main site of accumulation triacylglycerols is the cytoplasm of adipocytes. Adipocytes are the cell in adipose tissue, yes? When we want to use the energy from the triacylglycerols, we need to do 3 steps. The first step is the mobilization of lipids. It means you have triacylglycerols in the adipose tissue and the adipocyte, and you need to degrade the triacylglycerol to glycerol and 3 molecules of fatty acids. This process is called mobilization of fatty acids or mobilization of lipids. The second process is you need to absorb the fatty acid to the cell. Then you need to activate the fatty acid in the cytoplasm, and you need to transport the fatty acid from the cytoplasm to the matrix of mitochondria. And then the last process is the beta-oxidation itself. That's the place where you generate the reduced cofactors, where you generate acetyl coenzyme A. Yes? So these three processes, and we will go through them. So the first process is the process of mobilization of lipids. It means the mobilization of fatty acids in the adipose tissue. Enzyme that does this mobilization is called lipase, for it degrades lipids. And it's the hormone-sensitive lipase. It means this lipase is regulated by hormones. It do the complete lipolysis. It means that from one molecule of triacylglycerol, you gain 3 molecules of free fatty acids and 1 molecule of glycerol. Yes? There are some lipases in our body that, for example, chop only 2 fatty acids, and the rest is the monoacylglycerol. The hormone-sensitive lipase does complete lipolysis. Then the fatty acids go from the adipocyte, and they are bound to albumin. Albumin, that's the plasma protein that can carry many compounds. It can carry bilirubin, it can carry fatty acids, many drugs it can also carry. Yes? How is this enzyme regulated? Hormone-sensitive lipase catalyze anabolic or catabolic reaction. It's catabolic reaction. So it has to be activated by catabolic hormones and inhibited by anabolic hormones. Insulin, that's anabolic hormone, and therefore hormone-sensitive lipase is inhibited by insulin. And the counter-regulatory hormones, as glucagon, epinephrine, or cortisol, they activate hormone-sensitive lipase. I will remind you what we will do with the glycerol. Yes? Hormone-sensitive lipase releases 3 molecules of fatty acids and 1 molecule of glycerol. Yes? Last lecture, we spoke about the metabolism of glycerol, how it can feed the gluconeogenesis. So the glycerol is converted to glycerol 3-phosphate in a reaction catalyzed by glycerol kinase. And then the second reaction, we convert glycerol 3-phosphate to dihydroxyacetone phosphate. This is oxidation. This hydroxy group is converted to keto group, so it's catalyzed by dehydrogenase. Yes? So in these 2 steps, you use glycerol, and you feed with it gluconeogenesis. Yes? Do you remember it? All of you. So now back to fatty acids. The first process is done, that's the mobilization. The second process is we need to gain the fatty acids to the cell. You know, last lecture we spoke about glucose. The process is how glucose enters the cell are well described. Yes, we know precisely the GLUT transporters, the sodium glucose transporter. The transport processes of fatty acids is not so well described. Yes, we aren't absolutely sure what's the most important process. What do we know? What means this abbreviation? Short chain fatty acids. So those that have lower carbon count at 12, they can go by simple diffusion through the membrane. If they are longer than 12 carbon atoms, there are different transport systems in the membrane. Yes? Here are 2 examples. The first is fatty acid transport protein. The second is fatty acid translocase. You do not have to remember them, only know that fatty acids that have longer chain than 12 need to have some transporter. Yes? Those transporters do the facilitated diffusion. Yes? Then there are some other proteins that are secondary active. Yes? So now we have fatty acid in the cytosol. When glucose entered the cytosol, it was activated by glucokinase or by hexokinase. The same process is here. When fatty acid enters cytosol, it has to be activated. But here, it's not activation by phosphate. Here, it's activation by coenzyme A. You produce here the ester bond between fatty acid and coenzyme A. For the reaction, you need ATP. Sorry, here should be fatty acids. That's in check. So here it's fatty acid. Here is ATP. If you need ATP for the reaction, for a synthetic reaction, so what group of enzymes you will use? 6 group. It means ligases or synthetases. Yes? Therefore, the enzyme is called synthetase, and it produces acyl coenzyme A, and it's called acyl coenzyme A synthetase. So this is the enzyme for the activation of fatty acids. Yes? So the same role as glucokinase or hexokinase. But here you need 2 macroergic bonds. Yes? So for one activation, 2 ATPs you have to use, or 1 ATP, but you destroy both macroergic bonds.
What does MK say?
That's the fatty acids. It's from Czech. So I will correct it before I put it on the web. Yes? MK means mastné kyseliny. That's the same as fatty acids. And now, we have prepared fatty acid, and we want to gain energy from it. In general, we have 2 processes. One process with a major role is beta-oxidation in the mitochondrial matrix. The other possibility is to do the reaction somewhere else. Those processes you do not have to learn. That's, for example, omega oxidation or alpha oxidation, or it's also oxidation for a very long chain fatty acids, those that have more than 20 carbon atoms. Yes? So in the books you will read it. You can read in Harper, for example, the omega oxidation, alpha oxidation on endoplasmic membranes, then the oxidation of very long chain fatty acids in peroxisomes, but you do not have to remember it. Yes? Only know that the other pathways exist. Yes? Normally, less than 1% undergoes this. Yes? Under pathologic conditions, for example, if you have problem with beta oxidation, the ratio grows. Yes? So these reactions are normally important only for when you have some disease. Or for some tissues, they are also important, for especially in our brain, we have a lot of very long chain fatty acids. Yes? So if you would like to do the science in brain metabolism, then you will have to learn these pathways. For the normal energy metabolism, it doesn't matter. Why we have here these different Greek letters? Beta, alpha, omega.
It says in which carbon of the fatty acid it will.
Yes. And can you convert these letters to systematic numbers? Alpha means what?
Alpha means 1,
Second.
2.
Alpha means 2, beta means 3, and omega, last carbon. Yes? So, from now, I will tell you what's the fate of fatty acid if it wants to undergo beta oxidation. Yes? The major role. Beta oxidation takes place in matrix of mitochondria. And the acyl coenzyme A can go through the outer mitochondrial membrane, but it cannot go through the inner one. Yes? And therefore, there has to be some transport process, how to transport the acyl coenzyme A through the inner mitochondrial membrane. To do this, we have the carnitine shuttle. Yes? It consists of 3 enzymes. And the principle is that carnitine is small molecule. It has only 7 carbon atoms. Coenzyme A is very big molecule. Yes. And the carnitine can be easily transported through the inner mitochondrial membrane. The enzymes that transfer fatty acid between coenzyme A and carnitine are called carnitine acyltransferases. In some books, you can read carnitine palmitoyl transferases. Yes? Then the abbreviation is not CAT, but CPT. Yes? I think that in Harper, they use only the carnitine palmitoyl transferase. Yes? But the better way is to call it carnitine acyltransferase, for with carnitine shuttle, you can transport all fatty acids, not only palmitoyl. Here in the carnitine, you have the hydroxy group. And with this hydroxy group, can the fatty acid react to do what type of bond? When you have fatty acid and hydroxy group? Ester bond, yes? The first enzyme is called carnitine acyltransferase. Number 1, yes?
So is the CAT, is that different from the palmitotransferase?
No, it's absolutely the same thing. The same thing, you know. It was discovered that it transports palmitate. Therefore, the older name is carnitine palmitoyl transferase. But now we know that it can transport all fatty acids. Therefore, the new name is carnitine acyltransferase. But you know, the old habits are still very deep. So, I think that in this picture, you have carnitine palmitoyl transferase. Yes? And it's the same thing as carnitine acyltransferase, absolutely. So the first, carnitine acyltransferase number 1. So you have fatty acid in the cytosol, it's activated, so it's acyl coenzyme A. Here we have acyl coenzyme A. Carnitine acyltransferase takes carnitine and acyl coenzyme A and do the exchange. So it produces coenzyme A and acylcarnitine. Yes? Here is the ester bond. This enzyme is localized at the cytosolic site of the outer mitochondrial membrane. Yes? Then you have the second enzyme, that's the transport protein. Yes? This transport protein, translocase, is localized in the inner mitochondrial membrane. And the principle is that it takes the acylcarnitine from the inner membrane space, then carnitine from the matrix, and there's exchange. Yes? So 1 acylcarnitine in matrix, 1 pure carnitine between 2 membranes of mitochondria. Yes? So now you have what you want, acylcarnitine in the matrix. And to produce acyl coenzyme A, you have the third enzyme, carnitine acyltransferase number 2. This enzyme is localized in mitochondrial matrix. And it does the reverse transport. It takes acyl from carnitine back to the coenzyme A. The free carnitine then leaves the matrix to close the cycle, yes, to close the shuttle. And when the acyl coenzyme A enters mitochondrial matrix, there is only one fate for it, the beta-oxidation, yes? So here we have the scheme. Here we have the activation of fatty acids. First enzyme of the shuttle, carnitine acyltransferase 1. It produces acylcarnitine. Then you have translocase that exchange acylcarnitine to carnitine. And then the carnitine acyltransferase number 2 that produces the acyl coenzyme A. Yes? So if in the books you have carnitine shuttle, these 3 enzymes and 1 carnitine. Beta-oxidation. Beta-oxidation is a very simple process, for it's the same process as the Krebs cycle. Yes? So if you know reactions of Krebs cycle, you know also the reactions of beta-oxidation. In Krebs cycle, what we will take from the Krebs cycle is the cycle from succinate. For at the beginning, you have linear fatty acid with no double bond, and succinate is the same thing. What do you do with succinate in the Krebs cycle? Fumarate. By what enzyme? Succinate dehydrogenase. The cofactor is FAD. Here you have acyl coenzyme A dehydrogenase, and prosthetic group is FAD. You have fumarate in Krebs cycle, double bond. What's the reaction that you do? Addition of water. Here, second enzyme, hydratase, catalyzes addition of water. What's the product of the hydration of fumarate? Malate. What do you do with malate? Oxidation. Malate dehydrogenase. From malate you produce oxaloacetate. Coenzyme is NAD. This is hydroxy, the same as malate has hydroxy group. You do the dehydrogenation. Coenzyme is NAD, and you produce keto group. And the only different thing is that when you produce oxaloacetate in the Krebs cycle, you let it react with new acetyl coenzyme A. Here, you chop 2 carbon atoms away by the beta-ketothiolase, and you produce 1 molecule of acetyl coenzyme A. So in beta-oxidation, you have only 1 new reaction. Yes? The other one you know. So the first enzyme is acyl coenzyme A dehydrogenase. It catalyzes the production of double bond between alpha and beta carbon. It means between second and third carbon. Cofactor is FAD. And what is for us important, that in the matrix we have at least 3 different dehydrogenases. And they catalyze reaction depending on the number of carbon atoms. So we have acyl coenzyme A dehydrogenase for long chain fatty acids, for medium chain fatty acids, and for short chain fatty acids. So if you give to mitochondria, for example, palmitate with 16 carbon atoms, then you will use long chain fatty acid dehydrogenase. When you go to only 10 carbon atoms during the degradation, the second enzyme will take it. When you degrade other 4 carbon atoms, you use the third enzyme. So to degrade palmitate, you need all these 3 enzymes. Yes? For example, if you give to mitochondria fatty acid with 10 carbon atoms, you will start with medium chain fatty acid dehydrogenase, and then you will go to short chain fatty acid dehydrogenase. Yes? Why is this important? For you have metabolic defects, yes, impairment of beta oxidation, and the majority of these defects are localized here in acyl coenzyme A dehydrogenases. And you can have defect here, here, or here, yes? And it's important for the prognosis. You have to change the diet of the patient. And for example, when the patient has problem with this dehydrogenase, you will feed him with medium chain triglycerides. With triglycerides that have this number of carbon atoms, the fatty acids inside, yes? So therefore you should know it, yes?
When the enzyme for the long chain is not functioning.
Yes, if you have problem with this enzyme, then you will give the diet with the medium chain triglycerides. Okay. It means to feed this. Of course, then there is the problem that the patient has the accumulation of these fatty acids. Yes, it's a very big problem for the majority of fatty acids in our body has 16, 18 carbon atoms. Yes, but therefore we have the minor pathways, the alpha oxidation, omega oxidation, that they can help us. So that's the first enzyme. Second enzyme, you have double bond, you take water, and you produce on beta carbon hydroxy group. Hydroxy group can be oxidized to keto group by dehydrogenase. Here the cofactor is NAD. And then the new reaction is if you have fatty acid with 2 keto, then you want to remove these 2 carbon atoms and to produce acetyl coenzyme A. Yes, that's the end product of beta oxidation, acetyl coenzyme A. So the last enzyme is beta ketothiolase. The sulfur, it uses the sulfur in the coenzyme A to attack these beta carbon and here to destroy this bond. Yes. So it's the incorporation of new molecule of coenzyme A, and you produce acetyl coenzyme A and acyl coenzyme A that is shorter. Yes. So when at the beginning was 16, now we have 14. After the other rotation, you have 12, then you have 10, then you have 8. Yes? The only thing what you change is the first enzyme, the dehydrogenases. Yes? The other 3 enzymes are used still the same. So that's the beta oxidation. So you can say that in one rotation of beta oxidation, you have one alcohol dehydrogenase, the second is aldehyde dehydrogenase. Yes? So you look at it at books, but it's not in the test. Yes? Only the names that these pathways exist. Yes? For example, this omega oxidation is very similar to the process how our body gets rid of xenobiotics, foreign compounds. Yes? The foreign compounds very often also react with oxygen radicals that are produced by reaction oxygen and electrons from NADPH. Yes? So our body, this reaction is the same as the detoxification of xenobiotics. Yes? For the detoxification, you have special lecture in the third course. Yes? So in this course, you do not have to know it. Do you have questions? No questions? So beta oxidation, you understand. Yes? It's the Krebs cycle.
Why is the end product succinate and aldehyde? Like, shouldn't it be?
I really do not know why. So it's the reaction proceeds so. Yes, the omega oxidation means that from monocarboxylic acid you produce dicarboxylic acids, and somewhere you destroy the chain. So from, for example, 20 carbon atoms you produce 6, 6, 4, 4. And to all of them you will convert to dicarboxylic acid. Succinate is dicarboxylic acid with 4 carbon atoms. Adipic acid is dicarboxylic acid with 6 carbon atoms. But why this, we do not know. Yes? And in these pathways, very often there is not only one product, yes? For it depends where you break the chain. Yes? So you also can produce, for example, malonic acid, yes? Or glutaric acid. For these oxygen radicals are very dangerous compounds yet that can absolutely destroy the molecule where they want. So, no questions? So then you have break till 20. So now we will be speaking about ketone bodies. Yes, how to produce ketone bodies, how to degrade them. The first question is, what does it mean, ketone body? What compounds are ketone bodies? So there are 3 ketone bodies in our body. And they are called acetoacetate, beta-hydroxybutyrate, and acetone. Do you know their formulas? So, how looks like acetone? And then to give there the hydrogen atoms. So there's this unfortunately is the waste compound. So we need especially these first 2. So how looks like acetoacetate? How many carbon atoms has acetoacetate? 4. So here we have carboxy group.
It's ketone group. CH2 and CH3.
Yes. So this is acetoacetic acid. Without the hydrogen is acetoacetate. Yes? So you put 2 acetyls together. Yes? And beta-hydroxybutyrate or 3-hydroxybutyrate.
Oh, yeah, it's 4 carbon.
Mm-hmm.
There's a hydroxy group in that.
Mm-hmm. So here is hydroxy group. So that Thank you. So this is beta-hydroxybutyrate. So the difference between beta-hydroxy and butyrate and acetoacetate is simple. Oxidation or reduction. Difference between acetoacetate and acetone is also simple. You remove this. It's decarboxylation. But these compounds, you can say that they are water-soluble fatty acids. Yes? They are produced from fatty acids, and they are produced only in liver mitochondria. And why? For during starvation, in liver you have a lot of energy, lot of fatty acids that are degraded in beta-oxidation. So you will produce ketone bodies to feed the rest of the body. Yes. For the beta-oxidation, you saw that it's at the beginning it consumes 2 ATPs. Yes. And the only organ that has enough ATP during starvation is liver. So they can do the activation of fatty acids, they can do the beta-oxidation, and they will take these fatty acids, degrade to acetyl coenzyme A, and then they will convert the acetyl coenzyme A to ketone bodies. And these ketone bodies then can be used by the rest of the body. Yes? So you can say that they are pre-degraded fatty acids. Yes?
Why is one of them waste then?
What?
There are only 2 that are useful?
Acetone cannot be used in the body. Yes? So it's a waste product. It belongs to ketone bodies, but only these 2 can be metabolized in the cells. Acetone cannot be. Yes? So, in what situation you will produce ketone bodies? You produce it in liver, you produce it there during starvation. For the beta-oxidation is process that's localized in matrix of mitochondria. If we have very intense beta-oxidation, you produce a lot of acetyl coenzyme A, lot of reduced cofactors. And if you produce a lot of reduced cofactors, you will feed the respiratory chain, and you reach the maximal possible oxidation in respiratory chain. If you continue it in the beta-oxidation, you cannot produce more energy. Yes? So then the liver decides to produce some energy source for the other tissues. and that are ketone bodies. So to produce ketone bodies, you need in the liver to have a lot of energy and a lot of acetyl coenzyme A that cannot be used in Krebs cycle. Yes? For the respiratory chain is fed by beta-oxidation by the reduced cofactors from beta-oxidation. Yes? And other thing, why during starvation, to have the Krebs cycle, you need enzymes, but you also need to have the other substrate. That's oxaloacetate. And during starvation, oxaloacetate is used to produce glucose. Yes? So the situation in liver mitochondria during starvation is that the main energy source are fatty acids that are degraded in beta-oxidation. They produce a lot of acetyl coenzyme A, a lot of reduced cofactors. Therefore, the mitochondria can produce a lot of energy from these reduced cofactors. And oxaloacetate is taken to gluconeogenesis, yes, to produce glucose for the body. So in this situation, you have there plenty of acetyl coenzyme A that cannot be used in the Krebs cycle. So what to do with it? You will convert it to ketone bodies. Yes, so that's the situation when you produce ketone bodies. You are missing oxaloacetate, you have a lot of energy and a lot of acetyl coenzyme A. So the complete process is, you need the mobilization, yes? So you need to mobilize fatty acids by hormone-sensitive lipase. You need to do the beta-oxidation in a liver mitochondria, and you need to have the excess of acetyl coenzyme A, then you start ketogenesis. All these compounds are produced only from acetyl coenzyme A, yes? You incorporate in the molecule only acetyl coenzyme A, yes? And for acetyl coenzyme A is macroenergy compound, you have also energy for these reactions. There are 3 reactions of ketone bodies generation. The first is the condensation of 2 acetyl coenzyme A's. Yes? So you take 2 and put them together, and you produce acetoacetyl coenzyme A. Yes? That was this compound, only here would be the coenzyme A. Now it would be simply to take the coenzyme A from the molecule and to have acetate. Unfortunately, it's not so simple. And in the second step, you add 1 more acetyl coenzyme A to the molecule. And you gain the unique intermediate that's called 3-hydroxy 3-methyl glutarate coenzyme A, abbreviations HMG coenzyme A. This molecule has 6 carbon atoms. Yes? 2 plus 2 plus 2. Together 6 carbon atoms. And then in the third reaction, you cleave this molecule, you release the acetyl coenzyme A, and you produce acetoacetate. Now on the pictures, so the first reaction of 2 molecules of acetyl coenzyme A, and you form acetoacetyl coenzyme A. It's catalyzed by beta-ketothiolase, and you remember that this is the last enzyme in beta-oxidation. Yes? In production of ketone bodies, you do the reverse reaction. Yes? From 2 molecules of acetyl coenzyme A, you produce 1 4-carbon atom molecule. Yes? So it's the opposite reaction. The second reaction is condensation with the third acetyl coenzyme A molecule. And you produce the hydroxymethyl glutaryl coenzyme A. Yes, so glutaryl, it means 5 carbon atoms, and dicarboxylic acid. So 1 carboxy group, second carboxy group, 1, 2, 3, 4, 5 carbon atoms. And on third carbon atom, you have hydroxy group and methyl group. Yes? And also you release coenzyme A. And now in the third reaction, you only remove this from the molecule. Yes? This red is removed, so it means you remove this acetyl coenzyme A, and the rest of the molecule is acetoacetate. Yes, so for production of one acetoacetate, you need 3 molecules of acetyl coenzyme A. Yes? But only 2 of these molecules are used for the synthesis of them. Yes? The one is only added and then removed. But we have not only acetoacetate, we have also beta-hydroxybutyrate, and we have acetone. It's quite easy. For acetoacetate, if you do this decarboxylation, you produce acetone. There is no enzyme to do this reaction, yes. This reaction you don't want to proceed, but it's a spontaneous reaction, yes. So some amount of acetoacetate will convert to acetone, yes. So simple decarboxylation, acetone is waste product. You can do nothing with it, yes. It's water soluble, so it will be in your plasma, in your urine, yes. You can measure acetone there. And here the reaction between these 2 ketone bodies, between acetoacetate and beta-hydroxybutyrate, it's simple. Here you have keto group, here you have hydroxy group. So acetoacetate is reduced by NADH to beta-hydroxybutyrate, and the opposite reaction is oxidation. It's catalyzed by beta-hydroxybutyrate dehydrogenase. Yes? During the starvation, what compound you think is the most prevalent ketone body in the plasma and in general in the whole body? It means what's the proper end product of ketone bodies production? This, or this? What's the most prevalent? If you will measure concentration of these 3 compounds, the highest concentration will have. So who is for acetone? Who is for acetoacetate? And who is for beta-hydroxybutyrate? And who said nothing? So, one of you who said acetoacetate, why?
It's a reaction less. So
That's true.
but it goes spontaneously to acetone. That's why I thought acetone.
Yes, but it's, if there is no catalysis by some enzyme, it's quite slow reaction. It's spontaneous, but slow reaction.
Okay.
Why beta-hydroxybutyrate? Of course, our body is lazy, that's true. So why to have one more reaction if it's not necessary? So why beta-hydroxybutyrate? Some idea. Why?
Maybe the hydroxybutyrate can be oxidized to produce energy more. So it would be more abundant or something?
Yes, this is one reason why beta-hydroxybutyrate is the end product. In this molecule, you have one more NAD. So the peripheral tissues can gain more energy from beta-hydroxybutyrate than from acetoacetate. And the second reason is, what's the situation in mitochondria, in liver mitochondria, when it produces ketone bodies? What's the situation? It has plenty of reduced cofactors. Yes? So it has plenty of NADH. And therefore, if you have plenty of this, then you will push the reaction in this direction. Yes? So the end product is beta-hydroxybutyrate. It has the highest concentration in blood. First reason for this accumulation of this will push the reaction in this direction. And the second, for here, you have more energy for the peripheral tissues than here. Yes? So the end product is beta-hydroxybutyrate. If you have after meal, the concentration of beta-hydroxybutyrate is about 0.05. After a few hours of starvation, you have around 0.5. And the maximal value can be 10 to 20 millimoles, everything in millimoles. Yes? So you can have more ketone bodies in your blood than you have normally glucose during long starvation. Yes? What do you think is the side effect if you have a lot of beta-hydroxybutyrate in blood when the concentration is about 10?
When we use it, we get acetone, acetate, and also then acetone. Maybe we get acidic.
You became acidic. And why? Acetone is not acid. So why you became acidic when you have so high concentration of beta-hydroxybutyrate? I think that you said it, but only in... Do we produce butyrate? At the beginning, we produce butyric acid. Yes, beta-hydroxybutyric acid. This acid dissociates to butyrate. Yes, and if you look at the beginning, was fatty acid, long chain, and only one carboxy group. Yes, and from this, for example, with 18 carbon atoms, or it's better with 16. From this, with one carboxy group, you produce 4 carboxy groups. From 16 carbon atoms, you can produce 4 beta-hydroxybutyrates. Yes? So this is the example of proton-productive reaction. Yes? Production of ketone bodies is proton-productive reaction. From fatty acids, you produce 4 acids. Yes? It means 4 hydrogen protons. Yes? So the side effect during starvation is that you have acidosis. It means lower pH than normal. Yes? Due to these 2 acids, and especially due to this. How we will use the ketone bodies? Ketone bodies can be degraded in the whole body, but not in liver, and also not in erythrocytes and other cells that do not have mitochondria. Yes? So in all extrahepatic tissues, they can be used, but only in mitochondria. What's the principle of activation? So how we can use the ketone bodies is simple. The first, you need to convert acetoacetate to acetoacetyl coenzyme A. So the first possibility how to do this is to take coenzyme A plus acetoacetate, and you do the activation. But why you do not do this? Why there is other way how to use it? Why for the activation we do not use the normal activation of fatty acid? The activation normally needs 2 ATPs. Yes? And you do the beta-oxidation in liver and the production of ketone bodies. For in liver you have a lot of energy. Yes? And therefore, ketone bodies aren't activated by a reaction that is coupled with consumption of ATP. So there has to be other way how to do this. And the way here is that the source of coenzyme A is succinyl coenzyme A. Succinyl coenzyme A is intermediate of Krebs cycle. Therefore, the activation is in mitochondria. Yes? And in this reaction, you let react acetoacetate plus succinyl coenzyme A, and you produce acetoacetyl coenzyme A and succinate. Normally in Krebs cycle, how you change succinyl coenzyme A to succinate? Yes, so you chop the coenzyme A, and what you will gain? 1 GTP. So if you do this, you lose 1 GTP. Yes? But with the normal activation, it means fatty acid plus coenzyme A plus 2 ATPs. So therefore, we do this. For here, we need only 1 macroergic bond. Yes? So that's the way why we do this bypass in the Krebs cycle. We take the acetyl coenzyme, we take the coenzyme A from succinyl coenzyme A, and we put it to ketone body. And then the last reaction is simple. Acetoacetyl coenzyme A in mitochondria undergoes the last reaction of beta-oxidation catalyzed by beta-ketothiolase. Yes? So only this reaction is unique, and this transferase is not in the liver. Yes? Therefore, our hepatocytes cannot use ketone bodies, for they are missing this enzyme for activation. They can produce ketone bodies, but they cannot use them. How important is acetoacetate and other ketone bodies for our body? Yes. So during starvation, we have very, very high concentration of ketone bodies, and they became the main energy source for the body. Yes. But even under normal condition, some cells likes to use ketone bodies. Our cardiac muscle and kidney prefer normally acetoacetate to use it. Yes. Also, our brain, you know that our brain every day consumes about 220 grams of glucose. During long starvation, 50% of this energy expenditure can be covered by ketone bodies. And acetoacetate has one other role. If you have a lot of ketone bodies, you reach some maximal concentration, that's about 20, is the maximal concentration. Then it's wasting of energy to produce more ketone bodies. And this high concentration of acetoacetate, it means this is the signal that you have a lot of free acetyl coenzyme A in the liver mitochondria. This will block the mobilization of lipids. This will block the hormone-sensitive lipase. Yes? So the acetoacetate is inhibitor of hormone-sensitive lipase. Yes? So the hormone-sensitive lipase is not only regulated by hormones, but also by acetoacetate. And the regulation of ketone bodies, in the books you can read 3 steps, but only the last one is the pure regulation. The first is you need to have fatty acids. Yes? So hormone-sensitive lipase regulates the ketone bodies production. That's true. You need to have the beta-oxidation. Regulation of beta-oxidation, that's the carnitine acyltransferase 1. Then you need to have proper conditions in mitochondria. So you need to have a lot of energy, a lot of acetyl coenzyme A, and you have to have and you have to miss oxaloacetate. So in these conditions, you can produce ketone bodies. And then you have 1 regulatory enzymes in ketone bodies production. It's the second enzyme, is the enzyme that combines acetoacetyl coenzyme A plus acetyl coenzyme A. Yes? It's called HMG coenzyme A synthase. Yes? This enzyme is regulated by some hormones. Yes? Insulin blocks it, glucagon activates it. It's activated by high-fat diet also through some nuclear receptors. It's activated. And then there is one specific way how to activate it. It's activated by succinylation. If you add succinate on this molecule, it's activated. Yes, so it's similar to phosphorylation, but here not phosphorylation, here addition of succinate. Yes, so here we have 3 regulatory mechanisms. The pure one in this is this. These 3 only give the substrates to the production of ketone bodies. Yes. In beta oxidation, you have no regulatory enzyme. Here you have this one. That's everything.